can see it.
Okay, then I think we're all set.
Yeah, just for your information, there'll be audience attending live on YouTube, and I'll relay all of their questions to you. And how do you prefer asking the questions? Would you prefer it at the end, or would you be okay with
Probably at the end.
Okay, I'll let you know. And with that, let's get started. Thank you, Dr. Cassandras, for showing up today for your talk. And, hello, everyone. Welcome to this week's session on the Data-Driven Learning and Control Seminar series. And today's speaker is Dr. Christos, Professor Christos Cassandras from the Boston University. And he's going to present reinforcement learning-based receding horizon control with safety guarantees. A little bit more about Dr. Cassandras. He's currently a distinguished professor at the Boston University, and he's the head of the division of systems engineering and is also associated with the electrical and computer science engineering. And he's the co-founder of the Boston University's Center for Information and Systems. And he did his undergrad in Yale, and then he went on to Stanford, and then he did his PhD from Harvard. And later on, he was a professor at the University of Massachusetts Amherst before getting into Boston University. And his research is about discrete events and hybrid systems, and more on the cooperative control, like connected and automated vehicles. He also works on stochastic optimization and computer simulations with applications on sensor networks, manufacturing systems, and transportation systems. And he has contributed to more than 500 peer-referred papers and 7 books. And he has guest edited a number of journals. And Dr. Cassandra served as the editor-in-chief of the Transactions on Automatic Control, which is a prestigious journal in the controls community from 1998 to 2009. And currently, he's an editor in the Automatica. And he also contributes a lot to the Control Systems Society, serving as the president, vice president, and board of governors. And furthermore, he has given a number of plenary talks and a bunch of conferences like the American Control Conference, the CDC conferences, and the IFAC World Conference. And he's a recipient of a number of awards in the Control Systems Society, like the Control System IEEE Control Systems Technology Award and the Distinguished Member Award. And one of his books got the Harold Chestnut Prize for the best control engineering textbook. And he's also currently a chair professor at the Department of Automation at Singapore University. And without further ado, I let Dr. Cassandras take over.
Okay, thank you very much for the introduction. The title of my talk today is Reinforcement Learning-Based Receding Horizon Control with Safety Guarantees. And let me put it in context as soon as I can get this to work. Yeah. I believe that when it comes to complex multi-agent system types of problems, optimal control is a very appropriate way to formulate the problems, because we can state what objectives we have for a controller, as well as include a lot of constraints that our control must satisfy, both hard safety constraints and soft safety constraints. So on the left side, I list the pros and cons of the optimal control approach in this general class of problems. It can certainly lead to optimality, but the prices to pay are the difficulty in obtaining closed-form solutions when there are many constraints which become active. It is time-consuming to compute a solution to such an optimal control problem, so that limits its applicability to real-time problems. Often, we need to resort to simple enough models to allow our analytical solutions to be derived. And also, the solutions are frequently not robust to disturbances, meaning that if you made a mistake in how you selected certain parameters, or if you're operating in a time-varying environment, you have to resolve what is already a hard problem. On the other hand, we know that given a particular application and gaining an understanding of the specific problem, we can develop ad hoc real-time controllers, which are easier to obtain and can handle a lot of features such as nonlinearities, constraints, noise, and so on. Of course, when you choose this approach, you're going to be suboptimal, and it's actually hard to evaluate how suboptimal you are. And perhaps most importantly, for the types of problems that I have become interested in, there are no guarantees for constraints. So if you want to operate in a safe critical environment, this goes out the window. So what I'm trying to talk about today is to kind of bridge this gap between the ideal optimal control approach and the more practical real-time controllers that we often devise. And ideally, what I'd like to discuss is how we can combine optimality with safety guarantees and establish some sort of a trade-off. Obviously, we cannot work out miracles. Now, from my point of view, the motivation is what we call the Internet of Cars. It's the emergence of connected autonomous vehicles, which are many of them operating today. We call them CAVs because they allow the sharing of information among them through connectivity. And one of the nice promises of the presence of connected autonomous vehicles is the ability to move from a selfish to a social optimality. Selfish meaning that we each, as a driver, operate selfishly and choose to control our vehicle to achieve a certain driver-centric optimal point, whereas we could do much better if we could achieve a social optimum for the purpose of traffic control. And ideally, of course, if we can move into the domain of Internet of Cars, we could never stop, never need any traffic lights, which are expensive and hard to operate. And so the benefits of this approach are really inspiring. Now, coming back to this picture, I have on the left, once again, the optimal control approach, and on the right, a class of controllers that many of you, I'm sure, are familiar with, which we call model predictive controllers. Now, these are easier to obtain compared to pure optimal control approaches, but they are, again, suboptimal, and sometimes it's not easy to measure the extent of a suboptimality. Typically, for most of these controllers to operate, you have to linearize the dynamics of your system, and so there are linearization errors that creep in. The models are still too simple compared to some real-world systems we would like to control, and they can become fairly computationally expensive because, as you know, and as I'll try to also review this approach in a few minutes, they become computationally expensive because they're based on a receding horizon control view of the world. And so if you want to look too far ahead, then you have to pay the price in computation. The other approach is one that is based on what we call control barrier functions. These are easy to solve, the problems based on control barrier function controllers. They have a very attractive property known as forward invariance, which I will explain in a second. They allow for nonlinear dynamics and constraints. They allow for complex objectives, which need not have a nice analytical form. And they tend to be robust in noise in the dynamics. The downside of this approach is that they're, again, suboptimal, but as I will again describe, they allow you to quantify the gap between suboptimality and optimality in a much easier way. And they could be possibly conservative because they tend to be myopic. So the idea in what I'm going to be talking about is to try to combine control barrier functions and model predictive control to create controllers which can then be parameterized because each one of these techniques, MPC or CBF, is characterized by a bunch of controllers we typically tune manually. There is therefore an opportunity to use learning-based methods to learn how to tune those controllers in an optimal, ideally, way. So what I'm going to try to talk about today is this bridging of the gap between optimal control approaches and more ad hoc control approaches by combining CBFs, MPC, and reinforcement learning. The approach will be based on parameterizing, as you can see here. The MPC and CBF controllers combined, and then tune the various parameters that appear in those controllers through reinforcement learning. And then I will spend the second half of this talk to discuss how this approach can be used in the context of the Internet of Cars that I mentioned for the safe merging problem, one class of problems we encounter in the Internet of Cars. I will close with some description of the laboratory test beds that we're developing at Boston University so that we can move from the realm of just testing these controllers in purely simulation environments to testing them in a more real-world-like environment with mobile robots playing the role of the mobile agents. So let me start by overviewing CBFs, which may be the one component of these new controllers that you may be less familiar with. So in the context of control barrier functions, we look at the state space of the system, as you see on the left, as an environment in which we can define safe sets, and then we would like to force our system to always stay within the intersection of these safe sets. In other words, make sure that our controller always satisfies certain constraints. On the right side, what you see is the same type of picture, but with feedback control laws being applied in order to solve this problem rather than solving an open loop. So the idea here is to get the specifications that we're given for a certain problem, and then input into the feedback control space what is known or learned about the autonomous, typically, system that we're dealing with, so that we can create controllers which possess this forward invariance property that I mentioned earlier. What is forward invariance? It is the property of a controller to guarantee safety, in other words, remaining within the green area on the left at all times, at all future times, if you apply this type of controller, if, of course, you start in a safe state. And this is what control barrier functions can accomplish. So here's an overview of the CBF approach. The system dynamics that we can consider, as you can see, can be quite general. They need to be Lipschitz continuous, which is a technical requirement, but otherwise they are nonlinear, and the only limitation is that they need to be affine in control. Let me mention that even this can be relaxed in certain situations. Now, we are going to have a bunch of constraints, which are of this general form, and notice that these are constraints described by the state of the system. So given certain states in this state space where we're operating, we can define inequalities of this form that say this is what you have to satisfy in order to stay safe. The problem is that these are described in terms of the state of the system, not the control. What I'd like to know is what is the controller that can enforce these constraints? And this is exactly what the CBF approach does. It maps each one of these CBFs, which I'm subscripting here by K to indicate that there may be many of them, so that we can get an expression which tells us what is the control that can guarantee the satisfaction of these constraints. And it turns out that this transformation has a very nice, simple form, well-defined as follows. The CBF constraints, which of course depend on the individual state constraint that you see here, the BK, have this form. It's an inequality, and the first two terms are the Lie derivatives calculated along F and G, which are assumed to be known. If they're not known, that's another story. You have to then essentially learn the dynamics, which we can also do, but I'm not going to get into that now. The Lie derivatives, for anybody that doesn't know what they are of this general form. They're basically time derivatives of any function. Here it's b. In the general definition, it's some function v, along the dynamics. So you can think of f as being sort of the x dot here, which describes the time derivative of the state. So the first two terms here that you can see are well defined. The third term is any class k function, which is a strictly increasing function of this general form with this property, which you can select. And so you can see that this defines an inequality in U, by the way, linear, which tells you all of the controls that can guarantee the satisfaction of this constraint. So satisfaction of this condition, which allows you to calculate U, implies the satisfaction of this specification. I'm rewriting here the CBF constraint to emphasize this feature it has. It is linear in U, which is an amazing computational privilege that you have when you use this approach, because linearity is something that simplifies calculations a lot. So, in summary, this inequality provides a set of feedback controls, simply by solving it with respect to U, that guarantees the satisfaction of the original constraints for all future times if you start out in a safe state, which justifies what we call forward invariance. I emphasize, though, that this is only a sufficient condition. It says if this is true, then the satisfaction of the initial specifications is guaranteed. There's a theory that we have developed using the CBFs to apply particularly to autonomous systems, and I refer you to this recently published book, which describes details, a lot of proofs of the theoretical results, and there are 2 chapters at the end that describe a lot of applications. There are also some softer constraints that you don't absolutely have to satisfy, in which case there is a similar type of inequality that we can derive, as you can see here, which allows us to get as close as possible to a desired soft constraint, but not necessarily have to guarantee it. As an example, think of calves, which you would like to travel at this particular reference speed. So you would like to control them so as to make sure that this VI, the speed of calf I, is as close as possible to VREF in this quadratic sense. And the delta is a relaxation parameter that says, yes, ideally I'd like this to be 0, but since this is a soft constraint, I'll relax that and make my delta as small as possible. Returning to an optimal control formulation, you now see that we can solve this quadratic optimization problem in which we choose our controller in a specific way to get as close as possible to an optimal solution given some objectives. And at the same time, we can try to minimize this relaxation parameter, subject to the fairly general affine and control dynamics that I mentioned earlier, the CBF constraints, which characterize all of my hard original constraints, my CLF constraints, which characterize the softer constraints, and then, of course, control constraints on my particular feedback control law. So you can think of these 2 inequalities as being associated with hard safety constraints and soft constraints. In practice, to solve this optimization problem, you discretize time and you solve at each discrete point in time a quadratic program of this form, subject to the vehicle dynamics, the CBF constraints, and the CLF constraints I mentioned earlier. And it is important again to remind you that because of the linearity of these constraints in U, this makes this a quadratic program. Quadratic in the objective, linear in the controls. How do you solve that? As I said, you discretize time, and at every discrete point in time, you solve this problem, and it is easy to solve. I mean, typically, it's a fraction of a second. However, there is a practical complication in that you have to discretize according to some discrete time step delta t. How do you pick that? If you pick it too large, then you become quite inaccurate, and you can create infeasibility in that some of these quadratic programs, when they're solved, they do no longer guarantee the initial specification, because the initial specification is derived for a continuous version of this U. So if you make your discretization too coarse, then you may violate this constraint. So what we have actually worked on is eliminating the need for this very annoying selection of a discrete time step and replace it by what we call an event-driven approach. So we simply resolve this quadratic program only when needed. An interesting side benefit of this approach is that it increases the unpredictability of when you're going to update your controller, which contributes to extra security. And a discussion and description of how this is done by solving this CBF problems in an event-driven way is described in this recent paper. So I want to close this review of CBFs by talking about at least one of the problems that it can cause, which we know how to remedy, but we have to be careful about that. I show you again the basic inequality, linear in U, which tells me what are the controls that can satisfy the original constraints bk of x greater than or equal to 0. What if, though, this derivative here is 0, which can happen? Then I have no control over U. This second term is eliminated, and that's kind of a problem. To overcome this technical difficulty, the key idea is to keep taking derivatives of b, the function with respect to x, until the control U shows up. This is kind of a standard trick that is used in other parts of optimal control and optimization theory in general. So instead of having a single function, a single specification b of x, we start taking derivative of that, as you can see here, and create a sequence of these functions, psi, and we are then led to an extension of this inequality here indicated by star, which is called a high-order CBF constraint, and is of this general form, where the m here indicates the number of times you need to take a derivative until U shows up. And this is called the relative degree of a particular function. It is the number of derivatives needed so that eventually, with respect to this function, the control shows up. So again, the key idea here is to keep taking derivative of b of x. This defines a sequence of functions psi, not just the base control constraint, rather state constraint that we have here. And you have to enhance then your CBF constraint in this general form. Again, I have lead derivatives in my first two terms, except that I have to now take them more than once. Again, I have a class K function, which shows up for the m minus first of these functions. And this term is sort of like a residual term, which involves all of the remaining lead derivatives when you're taking more than one. But even though it may look a little bit tedious, it is fairly straightforward, because if you give me a specification B, I can always calculate all of these terms that you see here. And again, the linearity in the control is essential. So that closes my review of CBFs. What about MPC? I have a single slide here to review that, because I assume that most people are familiar with it. In MPC, what you do is you define a receding horizon, which is defined by a number of steps, of look-ahead steps that you look for. So if you don't want to look ahead, then this index h would be simply 0. But if you want to look forward, then you can select this number n. The larger it is, obviously this becomes more complicated to deal with, but it can be done. This is the terminal cost that you might associate with a terminal state that you need to achieve. And here, notice that we have already discretized our dynamics. So the dynamics can be also fairly general in terms of f. The state and the control are constrained within appropriate sets. And so does the final state here. And typically this f is taken to be linear. So there's a linearization that takes place to simplify the computation. However, if you solve this problem at any time step, h, then you derive a controller. And this controller is applied only at the current step. And that's the whole idea of receding horizon. You apply your control only for one step. And at the next step, you resolve the problem. And again, apply it to the next step. So ultimately, you generate a sequence of controls over your current time and up to the look-ahead time step that you wish to work with. I want to contrast this to the simple QP under the CBF approach, where essentially you can think of n is equal to 1, which is myopic. And this is one of the limitations of the CBF approach. It is myopic. It only looks one step ahead. That's nice. It's simple. And very often it works just fine. But it limits our ability to look ahead to the potential of creating infeasibilities. And the MPC approach is one way in which you can mitigate this myopic aspect. So our idea is to combine MPC and CBFs. However, there are various parameters in these combined MPC-CBF controllers that show up. For instance, when I mentioned in the CBF approach that you have to choose a class K function, that class K function depends on certain parameters. If you choose it to be linear, there's at least one parameter, the scaling parameter. If you choose it to be quadratic, there could be 3 parameters that you need to tune. And that leads us to the idea of tuning these parameters using reinforcement learning. So here's my one-page review of what reinforcement learning is about. We now enter a stochastic domain in which we designate actions and states by AK and SK respectively over a time step which is denoted by K, 0, 1, 3, and so on. Gamma is just a discount factor, which has some nice implications in terms of not allowing this this infinite sum to diverge. I'll omit this detail. This is a reward function that you have to select in order to solve this optimization problem, minimization of this criterion. This is a big deal because you have to pick what the reward function is. The good news is you can choose whatever you want. The bad news is you're on your own in picking a good reward function. If you don't pick a good one, then you get essentially useless results. The purpose of this optimization problem is to determine a policy that is going to, in this case, I say maximize. It could be minimized depending on whether this is a reward. Since I call this a reward, might as well talk about maximization. This is a trajectory of your system defined as a sequence of states and corresponding actions. And so what you do is you select a trajectory, you sample a trajectory, and calculate these expectations over many of these trajectories you pick. So imagine that you're just simulating your system and you just pick different trajectories over which can be simulated. But those, of course, depend on the policy that you choose. So the state is chosen from some distribution. The action is chosen also from some distribution, but that depends on the policy that you're working with. And then, of course, there's the system dynamics, which in this Markov decision process, because that's what it is, environment, are characterized by a transition probability function of this form. And the only last thing that we use in a reinforcement learning approach is the so-called state action value function, which is essentially the expectation calculation that you see here and is denoted by Q subject to whatever policy you choose. So in a nutshell, if you can solve this optimization problem, the maximization of this discounted sum of rewards, then you can come up with the optimal policy that is needed. Now, going back to our approach. As I said, it's a combination of MPC and CBF with some reinforcement learning thrown on top of it to tune the parameters. The system dynamics, as I said, are very general, but they are affine in control. The hard safety constraints are given by expressions of this form. For example, if you're in a robotic team autonomous environment, then these might describe collision avoidance constraints. The cost function that we use for our particular purpose has this form. So you can see the L here is arbitrary. It's a loss function. So we're now moving into a cost or minimization problem. A loss function where we can pick it to be as nonlinear and potentially non-differentiable as needed. So already we're moving away from the constraints of an optimal control problem formulation where your loss function has to be nice. In addition, notice that these indicator functions imposed on the hard safety constraints that we care for penalize you to infinity when you violate this constraint. Otherwise, they contribute 0. So again, this is a nonlinear way of defining your loss function so as to take into account the constraints. They are taken into account through this very simplistic, if you will, way. You go to infinity if you violate the constraint, so you essentially have a very bad policy because it maximizes the loss. and 0 otherwise. The goal of this parameterized MPC-CBF combined control is to, number one, learn the parameter vector theta in a feedback controller of this form. This is the controller that I want to define, but I now parameterize it in some fashion, and the parameters are described by theta. But in addition, I want to make sure that I always guarantee the safe features of the controller that I designed. So it's not just about solving a reinforcement learning problem for some ad hoc controller. It's about doing that, but at all times preserving the safety guarantees which are described by these constraints. How do we do that? If I return to the MPC problem, remember that there is a cost associated with every stage, every discrete time point, and it has this general form. Well, rather than using this general form, I'm going to impose a quadratic form in order to still capture the penalties associated with my state and my control, but I want to capture that in a quadratic way to simplify, obviously, the computation. These vectors, matrices that you see here, you can think of them as just weights. And the simplest possible form, they're just simply weights that attribute different importance to certain state constraints or control components. So before I move ahead, notice that these are, in general, parameter vectors, which have to be tuned in this cost function. In addition, if I solve my MPC problem at every stage by imposing these CBF constraints, then as I showed you in my review of CBFs, they're going to be of this general form. This is the high order CBF form, which includes this sort of residual forms. But notice, and this is important, that my class K functions here, which may show here and implicitly here, are also parameterized. So you get to pick what class K function you want. In the simplest case, we pick linear ones, but still, it is important to pick them with certain parameters that make this inequality be satisfied, but make it as tight as possible to overcome the potential conservativeness of the CBF approach. And I remind you that if you pick your controller to satisfy this inequality, that implies the satisfaction of this inequality. And you can see here the trade-off that these parameters capture. If you pick your parameters poorly, you can be very conservative, certainly guarantee this, but you're just way too conservative. If you don't pick them poorly, then you may violate or get too close to this inequality, which may lead to infeasibilities. The important thing is that these are parameters which the reinforcement learning component of this approach is going to allow us to learn. And again, I emphasize the linearity of this inequality in U. So there's also soft constraints, which I mentioned in this general formulation earlier. Again, there are learnable parameters here, which come through this function over here. And these are, again, parameters that the reinforcement learning approach is responsible to learn. And I remind you that this is a relaxation variable, which is to be minimized. So this is now the full-blown parameterized MPC-CBF optimization problem that we need to solve at every discrete time step K. I'm not doing anything here in event-driven fashion. This is the subject of ongoing research. So the purpose of this slide is to show you the complete problem with the presence of all the parameters that are to be learned. This is the cost function that is to be minimized. As we said earlier, this is going to be a quadratic that's going to be parameterized by these parameters over here. There's another set of parameters that apply to the choice of this relaxation variable. And then you see that the constraint to be satisfied are the dynamics, which can be very general and nonlinear, the control constraints, the hard safety constraints, which are captured through these CBF constraints, and the soft constraints, which are captured through these CLF constraints. I am circling here all of the parameters. I have a full problem here. If these parameters are specified, let's say in a baseline of solving this overall problem, I'm done. But what this approach, which is inspired by the need to learn these parameters, does is it adds a reinforcement learning component, which iterates on solutions of this problem by trying to improve the choice of these parameters. You can see that there's three types of them. The ones that apply to my soft constraints, the ones that apply to the cost functions of the MPC problem, and the ones that apply to the formulation of the hard safety constraints here. This gives you an architecture of the reinforcement learning approach, which I overviewed earlier. On the left side here, inside this blue box, you see an iteration which reflects the MPC-CBF controller, the receding horizon part. So we simply iterate over our receding horizon. There is a reinforcement learning algorithm which tells us what these parameters are going to be, which are going to influence how this MPC-CBF controller operates. And then we iterate over simple cycles here through a neural network architecture that essentially emulates what any actor-critic algorithm would do, so that you can update your policy, which is sampled according to, whose parameters are sampled according to this theta over here. And we iterate and we close this loop and this loop. And again, I remind you the role of these parameters. These are the parameters theta sub epsilon, sub e rather, that show up, as you can see here, in that they influence the relaxation parameters for my soft constraints. These are the parameters that characterize how I pick my cost function, different weights on these two components. And the last set of parameters here are the ones that show up in my CBF, the CBF component of the controller, the hard safety constraints and the soft safety constraints. So this is it. And what I'd like to do for the rest of this presentation is tell you how to apply this approach in a challenging problem of safe merging, as depicted in this little picture here, in a multi-agent control problem where the agents here are the autonomous vehicles. This problem has been looked at in the context of what we call vehicle coordination. Lots of approaches have been used. I want to emphasize that there are centralized and decentralized approaches. Our own work stated here in the bottom, which combines optimization with safety guarantees, is a decentralized approach. So the problem, in its most general form that I can think of, is depicted in this picture, where you can see that the one, at least, of the two merging roads can be curved so that we can capture the effect of curvature, which affects the dynamics of my vehicles, and also a component, the objective function, which is the comfort of the driver and the passenger. So you can't go too fast if the curvature is pretty high. So drawing this picture again, I show you here the general form of the dynamics that we consider, which are in two dimensions, x and y. The speed is here, and then this is the heading controlled by my steering and my acceleration for the vehicle. The control is shown here. It's the acceleration or deceleration of the vehicle, and then the steering angle, which obviously will affect the heading of the vehicle. And notice that these include nonlinear terms. What are the objectives? There are three. Number one, we'd like to minimize the time in traveling from the point you enter an area that we designate as the control zone. So this is the area within which we allow our vehicles to communicate with each other, subject to various communication constraints, as well as control the vehicles in an autonomous fashion, whereas outside this control zone, I can't guarantee that I can do that. Note that if I can minimize this time, I can improve the throughput of this control zone, which is a dual form of this objective. The second objective is to minimize the energy consumption. So this is going to be a function of my acceleration, which affects the energy. Actually, it can be a function also of the speed in a general form. And finally, we would like to make sure, since this is a two-dimensional model, that we maintain the position of our vehicles in the center lane. We don't want to get off the road, and we don't want certainly to start sort of oscillating around the median line of the lane that we're in. And this is done in this quadratic fashion. DC would be the distance from the center lane. The constraints. The first important safety constraint is the rear end safety constraint. It is a collision avoidance constraint, and it is expressed through ellipsoids that we position around our vehicle. And we would like to make sure that we do not violate each other's ellipsoids between our target vehicle I and the vehicle ahead of us, which we denote by I sub P for preceding vehicle. And notice that the axis of the ellipse depend on the speed. This captures the fact that the collision avoidance constraint is a function of the speed. If you're moving too fast, then I'd better have a bigger ellipse to allow me more time to respond. The vehicle limitations are given by constraints on the speed and the acceleration. The third constraint is the safe merging constraint, a very important one in the merging activity. So this is a constraint that says that if I have found, based on some sequence in which these are to merge, which can be as simple as first in, first out, but it can be arbitrary, we denote the vehicle associated with I by IC, the conflict vehicle. For example, could be 2 and 3. So as 3 is approaching the merging point, maybe the designated or the vehicle designed to conflict potentially with it is 2. So the first term in this constraint, you see it's expressed in the form of an inequality, is simply the distance between my two conflict vehicles when they arrive at this point, okay? These mu's are to take into account the fact that we're not operating in a strict one-dimensional environment. This function phi is any function you want, as long as it satisfies the fact that at time ti0, when we enter the control zone, this is 0, it's irrelevant. But most importantly, when you do get to the merging point, then the value of this phi function is a phi, which is a typical reaction time. So the idea here is that even though I formulate this constraint as applying to all times during which I'm traveling through a control zone, in fact, I couldn't care less about the distance, let's say, between 2 and 3 or 3 and 4, whatever it is, except at the time when we get there. So as long as I define any function that says that when you enter the control zone, this is irrelevant, and when you get to the merging point, you satisfy a standard constraint that says that something proportional to the speed minus a safe position distance must be greater than or equal to 0. So essentially, this distance must be mitigated by this term over here. And so this is how we formulate safe merging. This is a generalization of earlier ways in which we have formulated such safe merging constraints. The road boundary constraint is expressed in this simple form where basically you're just saying that you're trying to not ever allow your vehicle to move too far to the right or too far to the left when you're moving on this lane. Now, as I said, my job is to take each one of these constraints that I've been showing you here, that I've been labeling with 1, 2, 3, 4, and so on, and turn them into CBF constraints that tell me what is the control that I need to, for example, enforce this B3 or this B4. This can be done by the CBF component of this approach, which we've already talked about. I'm going to give you one single example of how any one of these initial specifications, indexed by K, which is of this general form, can be derived. So as an example, I'm going to use this B3 constraint, which is one of those constraints that says you can't go too far, you can't go off the road in a lateral direction. So this is precisely this constraint over here that prevents the vehicle from going off the road in this direction. How do I do that? Well, I take my B3, which has this form, and I take the lead derivatives. It's basically a time derivative. And the important thing is that when you take the time derivative of this, you get this expression. This comes out of the dynamics. But you observe that you run into this problem that I mentioned earlier. There's a zero coefficient of ui. Basically, ui doesn't show up in the derivative of this. Well, that's a problem, but we know how to overcome it using high-order CBFs. We differentiate again, and we derive with a second-order lead derivative the second-order CBF, which this time has the ui show up. In other words, this term is no longer zero. If it were zero still, I'd have to differentiate again. So in this expression, I have my class K function, which depends on the z1, which is the one that comes from the first derivative, which I just simply rewrote here so that we know what we're talking about. And these are expressions, second derivatives of a known function, second derivatives of a known function, and then the residual terms here. These basically, when you do the computation, that's what you get. So I just simply wrote it there. And these can be obviously derived once again with respect to xi. So this can all be derived. Again, it's tedious, takes time, but it's not difficult to derive all of these CBF constraints. Once you do that, you are in business to apply your reinforcement learning, which we show here. And this is done by training each one of our participating autonomous agents here. But since every autonomous agent may interact with the vehicle ahead of it, which is in this case this IP, and the vehicle with which you may collide at the merging point, which has already been determined, I need to train my vehicle with respect also to the behavior of these other two agents. So what we do is we choose baseline behaviors, essentially arbitrary according to some policy of these vehicles, and all three of them participate in this training process for NEI. So for NEI, there's going to be two more vehicles that have to be involved in the training process. The way in which these other two vehicles behave is chosen from what we call behavioral policies. In this particular case, what we do is we simply randomly pick some parameters to indicate how the performance of this IP and the IC is, but without any optimization of the parameters, just some random parameters. That could be bad. That's the whole idea. If you start out with poorly chosen policies, you will improve them by improving the parameters that determine those policies. The reward function, which is used in this reinforcement learning approach, is shown here. As I said, it's very important because if it's not chosen carefully, it can lead to ridiculous, useless results. The reward here is indicated more as a cost, so it's minus a loss function. And you can see a term here, which penalizes a component in the quadratic component in the control. You can think of this as energy, but not really. It's more like the desire to not accelerate and decelerate too much, to maintain your constant speed as much as possible. This is a penalty on the steering. You don't want to turn your wheel left and right too much. This is to force your vehicles to get as close as possible to desired flow speed. This is to minimize quadratic deviation from a desired heading. And then these last two terms are the interesting ones. This is a nonlinear and potentially non-differentiable function on the fuel consumption. And this comes from the literature. As you can see, it is a polynomial in both the speed and the acceleration. So it's a fairly complicated expression that if we were to use optimal control, an optimal control approach, it would be very difficult to deal with. And then finally, this is the constraint violation penalty, which every time, for example, a collision occurs between two vehicles, or you get off the road because you chose very poor initial behavioral policies, you get penalized. And so basically you learn never to do that again. These are some results. So this is what we call the baseline. So this is choosing standard human-driven inspired policies for a scenario of merging in which there are these four cars involved. And what I want to show you here is the fact that we violate our constraints. For example, this is an acceleration constraint, which is violated over here. And this designates the deviation from the median, which is also violated, as also shown here. So this is the CBF constraint for the right boundary of the road. The 0 level means you're within your boundary. Nope, you violated here. And this is where you violate your constraint for safe merging. So this may indicate a collision that may have occurred between 2 and 3 or 1 and 3, depending on where the conflict occurs. So this doesn't work. But as you learn, the parameters that characterize your MPC-CBF controller, you get into this environment, MPC plus CBF plus RL. So this shows the result of the trip through the control zone by these 3 vehicles. One is already gone, and safely they have all merged here. And notice that the corresponding plots here show no violation of any constraint. For example, here, the green curve indicates how my CBF constraint preserves the constraint. Same here. These are some tabulated results that show the performance in terms of average travel time, the desire to maintain U as close to 0 as possible, the fuel consumption, which can be quite complicated, and then the total infeasibility. This is the number of times that you violate your CBF constraints. And notice that there are improvements here, about 10 or 11, a small 10% type of improvement in the time, much more pronounced improvement in the U square metric and the fuel consumption, and most importantly, perhaps more safety. There's a 65% reduction in the number of cases where you violated a CBF inequality constraint. However, I want to emphasize that just because you violate the CBF constraint, that does not imply that you violate the original constraint. Because remember, this is a sufficient condition. CBF constraint is a sufficient condition. So if you're very conservative, you're going to violate perhaps this constraint quite often. For example, notice here that the 4 classes of behavioral policies we considered involve conservative, moderately aggressive. Well, when you're very conservative, you violate this constraint a lot. But that doesn't mean that you collide or anything. It just means that you're no longer able to guarantee safety. And this number of infeasibility cases is drastically reduced. There are a lot of open questions that remain, even though with the presence of the reinforcement learning component and the look-ahead capability that MPC imposes, we have been able to provide these improvements. There remains an interesting question as to how many calves do I really need to realize the benefits of my approach. Notice that everything I've talked about so far assumes that all the vehicles, all the agents in my system are autonomous. And obviously, we'd like to get away from that because we are going to have some human-driven vehicles to deal with. How do we integrate calves with other elements in the transportation systems like pedestrians, bicycles, and so on? How do we use economic control incentives in order to incentivize the compliance of, for instance, human-driven vehicles to achieve social optimality? There's this issue of, do we really want to continue assuming a system in which everybody drives their own vehicle and are responsible for it, when we know that the typical car utilization is only 4%? So that brings us into a whole domain of research, which is quite active, to study mobility on demand. And of course, what about learning online? Because the approach that I described to you is an offline approach where I train quite intensely. I mean, it takes time to train my autonomous system, and in particular, my various autonomous vehicles, to tune those parameters as I showed you. So I want to close with just a few parting thoughts on answering these questions. What about mixed traffic? For instance, in this merging approach, when a cab is approaching and is about to merge, if it knows that it may conflict with this vehicle and this vehicle, a human-driven vehicle, no longer an autonomous vehicle that I can trust because I've been cooperating with it, here I have to ask my question, can I trust the HDV to let me go first, since it looks in this scenario I'm a bit ahead of it? Well, I don't know the answer to that unless we can develop techniques which enlarge the class of problems in which all the agents in my system are autonomous and cooperating to one where only a subset of my agents are cooperating with me and the rest are non-cooperative. Not necessarily antagonistic, because most HDVs are not suicidal. They're not going to try to collide with you, but they're definitely not cooperating. So we know that there are benefits from connecting autonomous vehicles: enhanced safety, reduced congestion, reduced energy consumption. But what do we do when we don't have 100% CAVs? My position at this point, personally, is that there are three ways to go about that. One is to work hard on developing perception or learning-based models to better model the human behavior in these models. The other is to prioritize safety over performance optimization, and then try to make sure that we can optimize our system in potentially a way which eliminates the unpredictability of the human. And another way is to develop cooperation compliance mechanisms with economic incentives. All three approaches, potentially in conjunction, are very important. I'm just going to tell you a quick result that we have recently obtained on this approach, which is encouraging in that it says that sometimes you don't have to worry too much about predicting how humans behave. You can simply force them to behave in a socially optimal way. And this is easily depicted and theoretically analyzed in this maneuver that we call the lane-changing maneuver, in which the two vehicles which are green are CAVs and they can cooperate, and the red vehicle is a human-driven vehicle which may not cooperate. Notice that when it comes to this controllable CAV C to decide how to merge in this lane, it has two choices. It can go ahead of CAV1, or it can try to squeeze between CAV1 and HDV. And we can solve an optimization problem that says, supposing, given that this is the way to go, I can optimize the best way to achieve this maneuver. Given that this is the way to go, I can determine the optimal cost and control for this maneuver. If you evaluate these and compare them, you will find which one is better and choose it. But the important thing to observe is that case 2 is one in which the HDV behavior is irrelevant. Because if I choose to merge ahead of CAV1, likely it is that CAV1 will probably decelerate a little bit while you accelerate to let you go ahead of it. That will force the HDV to decelerate, but it has no choice. It has to decelerate so as not to collide with you. And this is how we can force a desired socially optimal behavior on human-driven vehicles. Theoretically, we can prove that the optimal cost of this nice merge ahead of CAV1 policy, which makes the HDV relevant, is monotonic in the distance between the two vehicles, this distance over here. And notice that this is not really linear, even though it looks so, but it can be shown that it has this monotonic behavior, which implies that there's a threshold right here in this example, such that if you operate in the left part of this threshold, then you merge ahead of CAV1, otherwise you merge ahead of HDV. The intuition is very clear. If the distance is large, then it's safe enough to merge ahead of the HDV because the distance is so large that it becomes essentially irrelevant how the HDV behaves. Unless it's absolutely crazy and you're very close to the threshold and it decides to accelerate like crazy to hit you when you try to merge ahead of it, it is basically safe to operate in this regime. So there exists an optimal threshold on the distance between CAV1 and HDV that determines this optimal choice. We'll close by showing you some pictures of our environment in the robotics laboratory at Boston University, in which we have implemented, if you go to this website on YouTube, you can see videos showing how we have applied our approach on these 5 mobile robots in this example that represent the merging problem. And most recently, we're developing a new laboratory in which our entire floor is going to be a video screen. This is a sample in which I show you this. The advantage of that is that you can project on the floor any landscape that you like, any kind of, let's say, city environment, urban environment, highways, whatever, and you can switch between them in seconds. And the additional advantage is that then you don't need a lot of these expensive mobile robots to operate, because in the virtual environment, you can barely see it here, but there is a virtual vehicle in the simulation of this setting over here. And so we can have our real robots interact with our virtual robots. For instance, this could be my autonomous vehicles, and this could be my HDVs, so as to create these scenarios in which we can further test our various approaches that I've been describing here. And at this point, I will stop, and thank you very much for your attention.
Thank you so much, Dr. Cassandras. There are a number of questions, and so yeah, I'll get started with them. So the first question is, someone would like to know whether it's possible to derive a bound on the control barrier function based solution in terms of optimality.
Okay, so this has to do presumably with the gap that I mentioned. So if I go, for example, to this inequality, or let's choose the simpler inequality here. Can I find a gap which tells me what is the slack between the conservative solution that I might get from this inequality and what would happen when I actually hit the boundary? The answer is yes, if you use the analytical solution to solve this problem. But once you bring in this reinforcement learning approach where my parameters are calculated based on some learning algorithm, I can only do that empirically. Clearly, the choice of this class K function is what's going to determine this gap. And I can make it, for example, very simple by choosing a linear function and then vary the single parameter of this linear function and tell you by how much you exceed this inequality or not, in order to show you the extent to which you are conservative. And that's important.
Thank you. The next question is, so when we consider more derivatives, so the input term can actually appear into the constraint, the control barrier functions constraint.
Yeah, as in this slide. Yes.
Yeah. Could the approach use Lyapunov functions to handle such a case? That's the question.
I think the short answer is yes. And I would add that this continuous differentiation is actually the way that we can overcome the limitation of the dynamics of the system being affine in control. I can introduce additional derivatives on my control that way. But to answer the first question, the short answer is yes.
Personally, I have a question over here. When we do higher order derivatives, I see that we switch between the lay derivative along G to F. In the just the CBF, there was one term. The first term was LF, and the second term was LG. But when we consider the higher order constraint, it's the higher derivatives are computed with respect to LF. So, like, is there like any intuition to understand what's going on?
Yeah, I think what you're saying is that if I look at this base form with a single derivative, the second term shows only a Lie derivative along the G part of the dynamics. But when I go to the greater than 1 degree here, there's a LF that shows up. That's the price to pay, because now some information comes in this component of the inequality that is due to the F dynamics. Does that answer your question?
Yes.
Yeah. So the intuition is that you need some information here. You don't need any information on the F, but the minute that you do no longer, if this is 0, basically, I need to know why is it 0, and how can I compensate for that? And the answer is by evaluating this derivative. And if it's 0, I need to get more derivatives in there until I can get this bracket term not to be 0.
Okay, yeah, that makes sense. The next question is, given that k class functions are linear, the parameterization of these functions refer to only the, does the parameterization refer to only the coefficients? And what should we expect from different types of k class functions in terms of conservativeness?
Yes, I think that's a valid question that I also have. So most of the time we limit ourselves to linear functions for the obvious reason that they're simple and they seem to work well enough in the practical problems that we have been encountering. But one should wonder, why not use a general polynomial function? Well, the obvious answer is you have too many parameters then that you have to tune. But once we've broken the ice by using this reinforcement learning approach, and we already know how to control a lot of parameters. In fact, when we first applied this approach here, this is the parameter vector. I was surprised that even in the simplest possible case, we need about 20 or so parameters here, because these are all vectors. So if you start introducing more parameters, you need to worry about more tuning, more learning, more complications, which are technical in nature, local optimalities and things like that. But I think this is a very valid question, and this is something that I would like to research more.
Thank you. And there's one last question about the RL algorithm that we use to solve the problem. Like in your flowchart, there is this RL algorithm that you use to generate a number of episodes, right? So the question is, does it require the reward function to have any properties such as continuity or differentiability?
Yeah, so the reward function that we used, I showed it to you here. Where was it? Oh, this is in the specific implementation. This is the reward function that we used. So you can see that it's chosen to have a quadratic nature for convenience. That doesn't really bother me very much personally, because these are all soft constraints. These 1, 2, 3, 4 terms are soft constraints. This is the fuel consumption. This comes out of a physics-inspired model. I have no control over that. If experts tell me that this is the best way to model fuel consumption, I've got to respect that and use it. It's got a polynomial expression, so that's not too bad. But typically in these models, when you decelerate, you do not consume any energy. This is not shown in this expression, but you do not consume any energy. So there's a non-linear discontinuity there, which can make things complicated, but so does this. This is a 0 or infinity type of term. So the purpose of this is to shock your reward or your loss when you violate a constraint, and to make sure that you don't do it again. Generally speaking, I don't think that the exact precise nature of these functions really matters that much as soon as you start using them in a numerical sense. So these are numerically based techniques. You just evaluate this term, this term, this term numerically, and then you try to learn from it. But I cannot definitively answer that question by saying, yes, it has to have these properties or not. This is part of the black magic of these learning techniques.
Thank you, Dr. Cassandras. And I think that's, yeah, that was the last question we have for today. And thank you so much for giving us this talk. It was wonderful.
My pleasure. Thank you very much.
Yeah,
And we'll see you in the near future, I hope.
yeah, definitely.
All right.
Thank you.
Okay. Bye-bye, everybody. Thank you for attending.
See you guys next week.